across the cold void, something impossible is happening. The latest data reveals 3I/Atlas, a visitor from another star, erupting with jets of water nearly 40 kilograms per second, all while stranded farther from the Sun than Mars. Even the Swift telescope caught a surge of OH molecules, evidence of liquid life, where space should be silent and dead. No previous interstellar traveler, not even Oumuamua or Borisov, has broken the rules this spectacularly. The consequences ripple through physics. Either our textbook on comet behavior is fatally flawed, or Atlas is showing us chemistry never seen in the solar system. So why does 3I/Atlas look so uncannily alive out here? And what exactly are we missing? The water mystery. 40 kilograms per second. That's the measured water loss from 3I/Atlas. Not at the warm heart of the solar system, but stranded 3.51 astronomical units from the Sun, where sunlight is too weak to coax water from most comets. The Swift ultraviolet and optical telescope caught the unmistakable signature of hydroxyl, about 1.35 times 10 to the 27 molecules every second, each one a fragment of a water molecule torn apart by sunlight. This isn't a trick of the instruments. Researchers stacked over 2 hours of ultraviolet exposures, ringing signal from the cosmic noise. The result is unambiguous. 3I/Atlas is venting water at a rate that rivals comets much closer to the Sun, rewriting what physicists thought possible in the deep cold. Normally, comets wait until they're much nearer, about 2 astronomical units or less, before water ice starts to sublimate in earnest. But the numbers from Atlas demand a rethink. At least 8% of its surface must be active to sustain this outflow, far more than the 3 to 5% typical for homegrown comets. The water isn't simply boiling off the surface. Instead, it seems to be coming from icy grains, tiny debris ejected from the nucleus. Each one a miniature steam vent drifting in the coma and flashing to vapor under faint sunlight. Laboratory studies back this up. Micron-sized water ice grains exposed to solar radiation, even at these distances, can sublimate efficiently. The process is subtle, but the numbers don't lie. 3 visitors, 3 stories, 3 interstellar visitors, 3 radically different stories. The first, 1I/Oumuamua, swept through in 2017 as a silent tumbling shard. Bone dry, no coma, no tail, not a single molecule of water detected. Astronomers watched in frustration as it faded into the dark, offering only its odd shape and baffling acceleration. 2 years later, 2I/Borisov arrived. This one looked and acted like a classic comet. Icy, volatile, shedding water and dust in the sunlight. Its coma and tail matched the familiar blueprints of solar system wanderers. Borisov was a comfort, proof that at least some interstellar objects play by known rules. Then came 3I/Atlas, and with it the rulebook fell apart. Instead of slow, steady rise in brightness as it neared the Sun, Atlas's light curve shot upward like a flare. The comet's brightness didn't just increase, it exploded, outpacing predictions by a wide margin. This wasn't the gradual thaw of surface ice. Something deeper, more volatile was waking up beneath the crust. The color told its own story. As Atlas brightened, its coma shifted from a usual dusty white to an eerie luminous green. That glow is the fingerprint of cyanogen. Cyan radicals lit up by sunlight. But there was more. Atomic nickel lines, rare and unexpected, flickered in the spectrum, adding a metallic edge to the comet's palette. Unlike Borisov, where cyan appeared early and faded gently, Atlas held back, then unleashed its green emission in a sharp burst, as if a chemical switch had been thrown deep inside the nucleus. Atlas stands apart as a new archetype, not dry and silent like Oumuamua, not comfortably familiar like Borisov, but hyperactive, chemically restless, and visually electric. Nickel without iron. That's a phrase echoing through comet science in July, when a very large telescope caught 3I/Atlas's coma lit up with atomic nickel lines, while iron stayed hidden. Spectra recorded as the comet coasted past approximately 2.8 astronomical units from the Sun show a metallic fingerprint that shouldn't exist. In every solar system comet studied so far, iron and nickel travel together, usually in a 10-to-1 ratio. On Atlas, nickel stands alone. Dr. Veronica Kubler, lead spectroscopist on the VLT campaign, became the lightning rod for this anomaly. Her calibration routines drew intense scrutiny, yet each new set of exposures confirmed the pattern. Strong isolated nickel emission, iron lines barely above background. Some modelers argue for fractionation. Maybe Atlas's parent disk split nickel and iron during formation. Others point to chemistry. In a carbon monoxide-rich coma, nickel can form volatile carbonyls that break apart under sunlight, releasing nickel atoms into the gas. Iron carbonyls, by contrast, are far harder to make and destroy. A third camp blames space itself. Cosmic rays and micrometeoroids could have sculpted a weathered surface rind, stripping iron while nickel accumulates in more fragile phases. Still others look to the comet's birth environment. If Atlas grew up around a thick disk star with odd metal ratios, the answer might be written into its core. No single mechanism fits all the data. For now, the nickel lines hang in the spectrum like a challenge, proof that Atlas's chemistry is stranger and more revealing than any comet seen before. The chemical cargo. Carbon dioxide takes center stage in the cargo manifest of 3I/Atlas. Near-infrared spectra from JWST reveals something almost unheard of. The amount of carbon dioxide outpaces water vapor, possibly making CO2 the dominant volatile in the coma. For comet chemists, this is a red flag. In the solar system, water is usually king. Carbon dioxide rarely gets top billing. Here, the numbers flip. Dr. Anais Marin, a comet chemistry specialist, points out that such a high CO2 to water ratio means Atlas likely formed in an environment much colder than the birthplace of most comets we know. Only in the deep freeze of an outer disk or under a dim, low UV star could so much carbon dioxide survive locked in the ice. The timeline of chemical release adds another twist. Cyanogen shows up late, weeks after the initial outgassing. In Borisov, cyan appeared early, rising with the first signs of activity. Atlas holds back, then releases a sharp burst, as if a chemical trapdoor opened deep inside. This delay hints at layered ices or exotic trapping mechanisms. With cyan locked beneath more volatile compounds, only free when the comet's crust fractures or grains are ejected into sunlight. The odd volatile mix, carbon dioxide-rich water pore, with a delayed cyan flare, draws a picture of a comet formed far from the warmth of any sun, in an ancient cold disk. What comes next? The next phase in comet science is already under construction. The Vera Rubin Observatory, set to begin full operations in late 2025, will scan the entire southern sky every few nights, catching interstellar visitors like 3I/Atlas before they slip away. Together with new instruments, these surveys promise not just more objects, but richer, faster data, chemical fingerprints, dust-to-gas ratios, and the first real-time alerts for rapid response. Astronomers are drafting wish lists. High on the agenda, tracking the emergence of iron lines in Atlas's spectrum as it swings closer to the sun, mapping dust color shifts and measuring the polarization of the coma to decode its structure. Fast launch concepts, miniature interceptors on standby ready to chase the next interstellar arrival, are no longer science fiction. This is a community effort, from seasoned professionals to backyard observers. Every new detection, every anomaly flag feeds into a growing database, a chemical census of the galaxy. The era of accidental discovery is ending. Now the challenge is to catch these messengers in the act, to turn fleeting encounters into lasting knowledge. The bottom line, at 3.51 astronomical units from the sun, 3I/Atlas was measured releasing around 40 kilograms of water per second, an activity rate confirmed by swift UV detections. This behavior, far beyond where most comets show such volatility, sets 3I/Atlas apart from both 1I/Oumuamua and 2I/Borisov. Archival spectra from the Very Large Telescope revealed strong nickel lines without detectable iron, and JWST data showed carbon dioxide likely surpassing water in abundance, findings that challenge standard comet chemistry. Despite these breakthroughs, the precise origins of the nickel anomaly and the processes behind Atlas's switch-on chemistry remain unresolved. As new surveys like Rubin prepare to skin the skies, The case of 3I/Atlas highlights how unexplained anomalies and careful measurement drive science forward. Each interstellar visitor is now recognized as a chemical record from another star, expanding our understanding of the galaxy's diversity, one documented mystery at a time.